let us look at another problem and see how to plot the Nyquist plot to investigate the closed loop system stability. The problem statement goes like this. Draw the Nyquist plot for a system whose open loop transfer function gh of s is given by k into s plus 1 divided by 1 minus s. Find the range of k values such that the closed loop system is stable. So as any other problem, here also we have open loop transfer function gh of s. Look at the open loop transfer function. Gh of s is k into s plus 1 by 1 minus s, and it is a type 0 system. We will write what is the magnitude and phase angle first of all. The magnitude is going to be, while substituting s is j omega, gh of j omega is k into 1 plus j omega divided by 1 minus j omega. And the phase angle expression is for k it is 0. So 1 plus j omega is a plus tan inverse j omega, and 1 minus j omega is a minus tan inverse minus of minus tan inverse omega. So phase angle is going to be 2 tan inverse omega. Minus of minus is place, already place I have, therefore it is 2 tan inverse omega. Now what is the Nyquist path for this particular transfer function? Since it is a type 0 system, the Nyquist path will have only 3 paths. And what are 3 paths? We have path 1, path 2 and path 3. So when I take path 1, it is from 0 to plus infinity. Path 2 is from plus infinity to minus infinity, but the radius is going to be infinity, or it is from plus 90 to minus 90. Then this is nothing but minus infinity to 0. So path 1, path 2, path 3. There is no path 4 because there are no poles at origin. Now, so what will be the mapping of path 1? Mapping of path 1 is a polar plot. So to draw the polar plot using this magnitude phase angle expressions, let us look at the table. So in the table I am going to have the 4 entries. When omega is 0, what is the magnitude? The magnitude is k. The magnitude is independent of omega. All the values it is going to be k only. Then when omega is 0, what is the phase angle? The phase angle is going to be 0. Because I have the phase angle expression 2 tan inverse omega, that is 0. Now, so when omega is infinity, again magnitude is k only, whereas the phase angle is plus tan inverse omega. Plus 2 tan inverse omega, therefore it is going to be plus 180 degrees. 0 and 180 degrees are starting and ending angles. So in between, if you take any 2 values, let us say omega is 0.01 and also 10,000, the corresponding values will be a plus 1 point something angle here, which is, it is in a plus angle, and here also have the plus angles, plus we have 180 plus 1. So which means we have these 2 angles in the first and second coordinates only. So when you look at the polar plot looks like this. I have to take 0 degree line. On this 0 degree line I am taking the point k. So this is the starting point. The ending point is at plus 180 degrees line, therefore that point is also k. All my values are positive values. So we have positive values, which means the graph will be like this. So what is the direction? Direction can be, it is anti-clockwise direction in this particular case. Now what is the mapping of path 2? It is 1 or more semicircles around the origin with r tends to 0. So that you can easily neglect it. What is the third path? Path 3 mapping will be inverse polar plot. We already have the polar plot like this. The inverse polar plot is a mirror image like this, but direction should be continuous. So with the polar and inverse polar plot, we are going to get exactly a circle with radius k. So everywhere you can see it is k. Now how to find the stability of the system? To find the stability of the system, look at where this Nyquist plot is intersecting the negative real axis or minus 180 degrees line. So we know that on 180 degrees line, minus 180 degrees line, plus 180 degrees line, both are same. That is the negative real axis, and this point is the k. Magnitude is k. Then what is the point? The point is minus k plus j0. So minus k plus j0. Now I am going to take 3 cases. So I am taking first case, k is 1. When k is 1, So the intersecting point is -1 plus j0, which is the critical point. We know that whenever the Nyquist plot passes through the critical point, the system is marginally stable or critically stable system. So the response will be oscillatory. Second case. So when k is greater than 1, when k is greater than 1, where will be the critical point? It is very clear the critical point is inside. When critical point is inside, then you draw the one line towards the left direction. See how many intersections we have and what will be the direction. And we know the direction is like this. So when direction is like this is anti-clockwise direction, and what is this n? The n is going to be 1. So n is 1 in this case. And what is Nyquist stability formula? Nyquist stability formula is z is equal to p minus n. Then how to find p? P is how many open loop poles that are lying in right half of the S-plane. Look at the open loop transfer function k into s plus 1 by 1 minus s. If you take minus common, that is going to be s minus 1, which means there is a 1 open loop poles lying in right half of the S-plane. The p value is going to be 1. P is 1. And from the plot it is n is 1 and the z is going to be 0, which is a closed loop, a stable system, which means there are no poles of closed loop system lying in right half of the S-plane. Third case, when k is less than 1. So when k is less than 1, we can look at here when you draw a line from the critical point, the critical point is away from the entire Nyquist plot. So when you draw this line, then number of encirclements is 0. So number of encirclements 0, and the p is already, we know that it is 1, and z is equal to p minus n, z is going to be 1, which means the closed loop system is unstable. Then what is the summary of all this analysis? So from 1 to infinity k value, the system is stable, closed loop system is stable. When k is 1, the closed loop system is marginally stable. So when k is in between 0 and 1, there exists a 1 closed loop pole lying right of the S-plane, indicates closed loop system is unstable.